In these video notes, we're going to talk about spherical geometry. So Euclidean geometry is the flat geometry we've been using all year long. So whenever you hear that word, that's just our not really our normal, but that's the geometry we've been dealing with for a while now. Spherical geometry is a non-Euclidean geometry, so it's different. It's not flat, and it's based around a sphere. The cross-section of a sphere is made when a plane passes through the center of the sphere. So if you look at our picture right here, this circle that is drawn, that is the great circle. One thing to take note of is that when we are dealing with a line on a sphere, that the line is that great circle. So around the edge, all the way around, is a line on a sphere. So how many cross sections on a sphere are there where the shape created is a circle? And that would be infinitely many, because you could make a cross section. It doesn't say it has to be the great circle through the largest part of the sphere. It could be any of the sections. So if we cut it across all the way. And if you didn't know, this symbol, this sideways 8, is the infinite symbol. How does, for number 2, how does the diameter of a great circle compare to the diameter of the same sphere? Well, we know that the diameter of the sphere will go from the center all the way out to the edge in both directions, and our great circle is in the center of the sphere, so they are the same thing. On this next one, I want you to answer, how does the radius of a great circle compare to the radius of the same sphere? So same type of question, except now we're talking about the radius of the sphere instead. Since the diameter is the same, that means that the radius will also be the same. Is it possible to have more than one great circle in a sphere? Okay, now let's think of that. The great circle, going back up to our definition, we know that it goes through the center of the sphere. So is it possible to have more than one great circle going through the center of our sphere? Okay, so this one is horizontal. But is it possible for us to have another one of those circles going through the center that maybe is not horizontal? And yes, it is. So we could have our sphere with the cross section going up and down instead. So yes, it is possible. One side comment that I want you to write on your paper is that we already mentioned that the line on a sphere is the great circle. So that's all the way around. Okay, so that means this segment, we already know a segment is part of a line, so that means that our segment is part of the great circle, and it is the shortest distance between 2 points on our sphere. So if I had a point up here and a point down here, my segment would just be connecting them together along that great circle. So on to the parallel line section, and this is a big section you need to understand of the difference with a spherical geometry. So is it possible to have two great circles? Remember, a great circle is through the center of our spheres, so they could be going up and down, across, but it's going through the center. Is it possible to have two of those great circles that never intersect? So one thing we can try to do is draw another great circle on our sphere. So remember, here's our center of our sphere. So we could draw our little oval around it, but look, they are intersecting, so that's not possible. If I draw it the other direction, there we go, that they're still intersecting each other, so it is not possible. So no, it is not possible. And we can kind of see in our picture over there as well. So is it possible to have two parallel great circles on our sphere? And that is not possible. So it's pretty much the same question, just worded a little differently. Now remember, a line on a sphere is the same thing as our great circle. So is it possible to have two parallel lines on our sphere? And that would be no, that it's not. So let's make a note of that. And that is different from Euclidean geometry in a big way, because Euclidean geometry can have two parallel lines. So just remember that our parallel lines in Euclidean geometry, so that's our old geometry we've been using, never intersect. But in our spherical geometry, it's not possible to have parallel lines on a sphere. The next thing we're going to talk about is triangles on a sphere. So a spherical triangle, 3 points on a sphere that do not lie on the same great circle determine a spherical triangle. So if you notice, you've got 3 intersection points on here. And it's created by 3 intersecting segments. So 1, 2, and 3. All right, so the part that is different, if you look at the angles in those corners, it looks like it's a little curved because our lines are not perfectly straight on a flat surface like we do on a piece of paper. So triangles, or the angles in a triangle, the sum of those for spherical geometry is that they will be more than 180 degrees. And that is way different than Euclidean geometry, because Euclidean geometry, they are equal to 180 degrees. So remember, the angles of a triangle in Euclidean geometry, the sum is equal to 180 degrees. But for our spherical geometry, it's going to be more than 180 degrees. That's one big difference right there. All right, so because we could have angles that are more than 180 degrees in our sphere, this is kind of the reason why. So if you look at this picture right here, we have the North Pole up here at the top. This is the equator around here in the middle. So if we connect the North Pole with 2 points on the equator, so those are right there, what do we know about the intersections of the lines with the North Pole and the equator? So what do we know about those angles right there? And if we cut our sphere in half, and then we draw a line directly from the North Pole straight down to it, that's creating a 90-degree angle right there in the corner. You do that with pink instead. And that would be the same thing on this other side. So how many 90-degree angles would we have? We would have 2 angles that are 90 degrees. And since we have 3 angles in a triangle, we already have our 2 90 degrees, which means that we already have 180 degrees when we add those together, which means that whatever this other angle would be would make it more than 180 degrees for the size of our triangle, so the angle sum. All right, so kind of the same thing, except now we're going to think of a tennis ball. So you're still thinking of a sphere. And what we are doing is we are cutting the ball in half. So think of right down the middle. We can think of like our great circle. Then cut it in half into quarters again. So think of straight up and down. So you kind of have 4 different chunks. You have these 4 different pieces. So each quarter produces a spherical triangle on the surface of the ball. And what are the measurements of the angles of this spherical triangle? So since we are coming straight down and straight across, each of those are 90 degrees, which means that all 3 angles would end up being 90 degrees, which is definitely way different than with our Euclidean geometry, where only 1 angle could be 90 degrees, because after that it would end up more than 180 degrees, and it can only equal 180 degrees in a Euclidean geometry triangle.